How did the solar system form? Well, a lot of people are believing a nonsense story about the solar system forming and don't even realize it because this story is being taught as if it's scientific, even though it contradicts physics. So, here to talk about with me is Jack Vann Kean. Welcome, Jack.
Rebekah, thank you so much. It's great to be here again.
Thank you. And so, for those who don't know you, can you tell a little bit about how did your background working in the oil industry as an engineer prepare you for answering these types of questions about the solar system?
Okay. In oil and gas, we deal with uncertainty all the time. We have to quantify it, identify it, figure out how to mitigate it. Examples might be should we spend $10 million to shoot seismic before drilling 5 wells? Or it might be running a reservoir physics-based model, evaluating the output and understanding what data we need in order to constrain that output further. So those are some of the things in petroleum engineering that sort of lend themselves to the solar system and where the solar system came from. And radiometric dating, certainly uncertainty is one of the key issues.
Okay, great. Well, let me pull up your slides, and I'm looking forward to hearing to what you've discovered about this.
All right. One thing I've noticed when people talk about the age of the Earth is why is it important? And there's sort of two perspectives. One is the materialistic or atheistic perspective. All atheists believe in billions of years, biologic evolution, and the Bible is false. And if you take away billions of years, then you take away biologic evolution. On the other hand, it's a little different for say, Christians. There was a 2022 survey that I saw that said about 75% of the respondents affirm billions of years. The issue for Christians is if one accepts billions of years, that means that the dinosaurs are millions of years old, and that the dinosaurs came before man. And that means that death was in the world before Adam, which contradicts the basic Christian theology of original sin, that Adam sinned, that's how death and sin entered the world. And of course, Jesus is the mitigation for that. So what Christians normally don't believe is that billions of years are an attack on the cross. And it's not just a Genesis issue. You also have to toss, if you believe billions of years, then it calls into question a number of verses in Exodus, Romans 5, 1 Corinthians chapter 15. So it's a very important issue for both materialists and Christians.
Well, now a lot of people are going to hear that and say, well, but science has shown that it's billions of years old. So how are you ignoring science in order to, keep theology nice and neat the way that you want it?
So last time we talked, I went through the lead radiometric dating technique and pointed out the uncertainty in it that results in uncertainty in the answers. And so that is what I would like to build on today in talking about the solar system formation, because the nebular theory, as it's called, that's where the solar system is believed to come from, is directly related to the assumptions that are used in radiometric dating.
Yes, and for those who think that young Earth creation is outlandish or, impossible because of science, check your own backyard. Are you believing this, nebular hypothesis about solar system formation? Because if you are believing something anti-scientific. You're believing something that contradicts scientific observations, as we'll get into in a little bit.
Well said. So let's start with the ancients. You've probably heard of Alexander the Third. He's also known as Alexander the Great. The Romans liked that fellow, and so they gave him that moniker. I want to read a quote to you from a historian A.B. Bosworth, and he's talking about the early days of Alexander's reign. No connected account survives of the first few days of Alexander's reign. There are scraps of epitome and random flashbacks from later history, but most of the crucial details are irretrievably lost. There is infinite scope for speculation and imaginative reconstruction, but the sources themselves allow very little to be said. We must be prepared to admit our ignorance, however galling that may be. So, what was Bosworth talking about the first few days of Alexander's reign? Well, his father was assassinated, and one of his father's wives, Cleopatra, was also murdered along with an infant baby. The ancient sources, and by the way, the main ones are Arrian and Plutarch, and they were writing about 400 years after the fact. And so there was a question, who was responsible for these deaths? And just bear in the back of your mind that the Macedonians were very Darwinian in their approach to ethics. So suppose, Rebekah, you were to make a movie and fill in the gaps of what we know in the narrative. How would you portray Alexander the Great? As a paranoid, drunken warlord, or as a visionary, philosophical poet king who trained under Aristotle? So that uncertainty, those gaps in the history, open the door to circular reasoning. And so the obvious example is to say, he was paranoid and barbaric because he murdered his father and wife. Or he murdered his father and wife because he is paranoid and barbaric. So we'll talk a little bit more about circular reasoning and get back to this example at the end. So the age of the Earth, when we met last time, I said the age of the Earth is unknowable using radiometric dating, and that radiometric dating ages are non-unique. So today, when I use the term radiometric dating, I'm referring specifically to lead radiometric dating, just like we talked about last time I was on. And it's built on the solar nebula theory. And just a couple things about it. It's not like an instrument. Like we can get a decibel meter and say go to a football game, and the decibel meter is calibrated for a range of say 30 to 130 decibels, and we can actually measure the crowd noise. Radiometric dating is not like that. Radiometric dating is more like making a forecast from what is known now back in time. It's very similar to, say, just for example, in the future, making a forecast for inflation. We have knowledge about right now, and we have to make assumptions about the future. So where we're going is, I'm going to suggest that the solar nebula theory is either false or needs unknown physics to maintain its viability. And then that leads from that conclusion that U-235, U-238 assumption and radiometric dating is circular reasoning. So that's where we're going.
Very cool.
Oh, all right. So solar nebulae, we're just reading here, the solar nebular theory is used to support 235U, 238U assumption and radiometric dating. What evidence supports the solar nebula theory? So
now, can you explain to people really quick what you mean by that the solar nebular theory is used to support that assumption? Because a lot of people have the idea, and I know you talked about this last time, but for those who didn't watch it, what is that, what are they building that assumption on? Like, I mean, because a lot of people think, oh, radioisotope dating, we know that this, look, you can't change these decay rates. It's known. This is like incontrovertible. So what's in question here?
What's in question is the assumptions that go into the radioisotope dating model. That's the question. The assumptions presume billions of years based on the solar nebular hypothesis. And when those particular input assumptions are used, applied to the model, they result in 4.5 billion years. So the question is, really, is there valid support to make that assumption of U-235, U-238 as the initial isotopes in the model?
Okay. And just to make it clear, you're not saying that uranium-238, 235, you're not challenging the rate of decay. You're challenging,
No.
We're not challenging the rate of decay. We're challenging the initial starting conditions. And you're saying that is supported completely on the assumption that this nebular hypothesis is true.
Well said. Well said. We're not challenging the model. It's the assumptions that go into the model. Okay. Just to sort of give a little context, I've got a few slides here on context before we get directly to the solar nebular theory. The purpose of this slide is to illustrate the difference between accuracy and precision. So if you look at the graph over on the right, you'll recognize a target. Increasing precision as you move to the right, increasing accuracy as you move up. So if you look at the lower left target, if we're a marksman, we might say we don't have very good precision and we're not very accurate. We got some more practice to do. If you move over to the right, you see how that's the shots are clustered in a place you could say, well, we've got good precision, but we're not very accurate. And then you can see the target in the upper left corner. Obviously, you would say something about, well, you're tolerably accurate, but not very precise. And then the upper right, you're both accurate and precise. Precision sort of has to do, you could remember by saying repeat is tight, accuracy, you would be more concerned, average is right. And the key thing for accuracy is you have to have a target. You have to have a bullseye. You have to have a reference. And there's no reference for the lead age of the Earth. The accuracy is unknown. So going to this next slide, the point here is that when we see these ages, they're not direct observations, they're model-dependent outputs, and the display is a bit deceptive when it comes to accuracy and precision. So the way this works, or the way at a high level radiometric dating works, take a meteorite sample, because meteorites are believed to originate when the Earth was formed. Run it through mass spec, and you get a report, and the report is actually a measurement of the isotopes that we measure today. And when those measurements are done, the lab work is outstanding. Repeatability, the sensitivity of equipment, the procedures on the lab work is all outstanding. Then those isotopes are plugged into the lead-lead radiometric model, which that was pretty much what we exclusively talked about last time. And then the result comes out. You see, here's an example here. There's a date, and then there's a date error. And it appears to be an error of accuracy related to years, but it's really not. It's really a precision error based on the laboratory measurements of isotopes. So to be a little charitable, it's a misleading way to express the data. All right, this is you probably remember our friends from our last talk, those vaguely familiar gentlemen, and who spilled the milk. Just as an example of uncertainty, what led to the conditions that resulted in the milk being spilled. So the way to think about radiometric dating is to view it through the lens of uncertainty. There are the initial conditions at the time of what's called crystallization, where the isotopes first became crystallized. That's unknown. There's the transient conditions. What happened between the initial conditions and where we are today? Now, there is no observable, measurable facts at the time of initial conditions. There are no measurable, observable facts at the time of transient conditions. We can't send an instrument back in time to take measurements for us. The only thing we know is the current conditions today. And I sort of represented this at that bottom right-hand side. This is data from Claire Patterson's 1956 paper. He was the first one to calculate 4.5 billion years as the age of the Earth. And his methodology is, at its core, still used today. So uncertainty is the point. Okay, so let's build a little bit upon that. In the center of the screen is the lead-lead radiometric dating model. It's a model. It's a forecasting tool, if you will. On the bottom, there's our current conditions, the isotopes that we can measure from meteorites today. That's an input. On the left are the choices for what variables to use at initial conditions. So at the top, I've got U235 and U238, which is the standard. And if you use those initial conditions, you get the discrete answer of 4.5 billion years over on the right-hand side. Well, if there are some daughter isotopes present, that next row down, there's 4 isotopes, for example. Depending on the amounts of those isotopes, there are ratios of initial condition. An answer using the lead-lead radiometric dating model is 100 million to 4.5 billion years old. And then down at the bottom, if we use even shorter lived isotopes, and I've got 7 lived there, plug them into the model, it's possible. It's mathematically a range of 6,000 to 4.5 billion years is possible. And I know our materialist friends are probably saying, no, this can't be, this is bogus. I just suggest that just make the calculation yourself. Just build a numerical model and make the calculations on your own. So again, the point of this slide is that various assumptions result in a range of forecasts from 6,000 to 4.5 billion years. Or to say it another way, the results are contingent upon non-testable initial conditions. Okay. So we want to evaluate the solar nebular theory using logic, not ideology. We want to use observational experimental science. What I mean by that is we want to use gravity, thermodynamics, and conservation laws. So here's a table. This is based on some work that was done by Karl Popper. And what he said that a valid theory needs to be predictable and falsifiable. And so in this table, for example, observational, we deal with rules. For example, an apple tree falls down, or an apple falls down out of a tree. That's our observation. When we get to the experimental, we're going to come up with a law and say, well, that apple falls at 9.8 meters per second squared. Therefore, we can predict when an apple in a tree does fall, it'll fall at 9.8 meters per second squared. What Karl was saying, Karl Popper, was that you have to have a theory that's falsifiable in order for it to be a valid theory. Well, what would be falsifiable? Well, if one day we went out and the apple fell up, we would then falsify our theory. That's what he was saying. Next level, model-based inference. So you're going to be dealing with an extrapolation to the past or future. You're going to have to make a lot of assumptions. This is going to be sort of in the realm of theories, moderately predictable, moderately falsifiable. The next, an example of that might be Pangea. That is an extrapolation into the past using a model of plate tectonics based on observations made today around geology and paleontology. So that would be an example of a model-based inference. Next level is speculative. This is where you get into it's not observed, it's not tested, it's not falsifiable. This is going to be more conjecture, sometimes circular logic. Variables are often to match the results. Really, I had to look this up because I had forgotten. A really good example of this is Alan Guth wrote a very important paper in cosmology in 1981. He's the gentleman that first proposed inflation. And he proposed inflation as a way to allow all the universe to come into thermodynamic contact to explain the cosmic microwave background. And he admitted as much, that his inflation was just to fit the model. So that would be an example of something being speculative. And then, of course, metaphysics. This is your claims and your naked assertions. And I know you've come across this quite a bit in your research with respect to biology. And these are generally non-falsifiable. The claims conform to a worldview. Now, over on the right-hand side, I added a legal analogy, observational, experimental. We go to a jury, it's beyond a reasonable doubt. That's our standard. Model-based is circumstantial, forensic reconstruction. Speculative is we don't even get to a jury because a grand jury denies indictment. And then, of course, metaphysics would be something about, a lawyer wanting to opine about constitutional philosophy for a murder trial. So just to put that in mind, this is the framework we want to use to evaluate solar nebula theory. All right. Once again, I've kind of covered this top part that There's a range of forecast model outputs that are a function of the inputs. And so here's the question we want to address. Solar nebula theory is used to support 235U and 238 assumption and radiometric dating. What evidence supports the solar nebular theory? And this is what we want to do is beyond a reasonable doubt is the standard, because I've heard more than once that 4.5 billion years is an unassailable fact. So that's the standard we're going to look to judge this by. Or is it circumstantial evidence? Or is it the grand jury declines indictment? All right, so this is where we're going. We've touched on the context. And now we're going to get into the solar nebular theory itself, starting with, well, what evidence supports it? Okay, here's our familiar radiometric dating model there on the right. We've already talked about that. And I've added two boxes to the left to encompass the solar nebular theory. There's really three issues. How does a star form, a protostar? How does it ignite? And how do planets form? So you sort of have to answer those questions to provide an entry into assuming U235, 238 as your initial conditions for the radiometric dating model. Did you know that the origin of the solar nebular theory is metaphysics from the 18th century?
Really?
Immanuel
What do you
Kant,
mean? Mm-hmm.
Immanuel Kant, he was a German philosopher who lived in the 1700s. And I've got a quote from him. Matter immediately endeavors to form itself. This body at the center point of attraction has become the main piece of planetary structure through the quantity of its collected matter, is the sun. The planets are formed out of particles that have precise motions as circular orbits. This is sufficient to have insight into why the motion of the planets is approximately circular in form and their orbits are on one plane. And it's real interesting here because he starts off with a metaphysical argument. Matter immediately endeavors to form itself. Matter is anthropomorphic. He's using scientific language to mask his philosophy. You mean matter endeavors on its own? It has consciousness to endeavor? So a metaphysical statement, but he ends with an observation. The planets have circular, their orbits are circular in form and their orbits are on plane. So consensus science runs all the way from observational to metaphysics. And it's real interesting. The observations he made are still the observations that are used to support solar nebular theory.
And for those who are in the chat, because there's a lot of people in the chat saying, oh, I guess Rebekah knows more physics than the physicists who came up with the nebular hypothesis. Look, I don't know physics at all. Never even had a physics class, okay? But what we are saying about what we're getting ready to talk about with the physics problem, this is something easily Googleable. And this is not a creationist thing, okay? So you can look it up right now and you can see the physics problems involved with solar system formation on basically just mainstream science sources, okay? So the question is, why then do people still believe this nebular hypothesis, even though it does contradict physics that we're going to get into and talk about. It's because of the metaphysics. That's what Vann is talking about, that this has, there's metaphysics involved. So if you have a contradiction in physics, but you don't have an alternative theory, then you're like, well, we don't know how it happened, but we know it happened. And so this is, that's what keeps it in place, even though it has physics problems. Would you agree with that, Vann?
Yes, I do. And thank you to the folks that are watching and commenting. I just ask for a little patience. I'm going to run through the physics that we're going to be talking about, and actually quoting mainstream physicists, and to show that it's not just Vann's opinion. What we're talking about, just like you said, Rebekah, is findable using Google. So thank you again for commenting. Please just bear with us here a little bit, and we'll get into some physics and have some fun with it, hopefully. Okay, so we've seen this, our little representation. So the first question is, what do we see today that supports the solar nebula theory? What are its fingerprints that we might observe today? And so down on the lower right-hand corner, I list 3 things there, and that's what we're going to talk about next. So the first thing, let's just run through the basics. What is the solar nebular theory of how our solar system came to be? The idea is that there were stars, they supernovaed and created elements, forming this molecular cloud, which collapsed under the influence of gravity, forming a protostar at the center of a rotating disk. Dust particles aggregate into planetesimals. Planetesimals aggregated into planets. The sun ignited. Self-sustaining nuclear fusion that we observe today. Solar wind cleared out all that gas and dust that didn't form into planets. Asteroids remain from planet-forming material. Meteoroids are asteroids that strike the Earth. And then so the lead dating relies upon meteorites for its material for inputs into the model. So just a basic, this is the standard, by the way. See, this is the basic college textbook. This is Seeds and Backman, Foundations of Astronomy. And so I'll refer to it here and there as we go on. And by the way, this is a classic. This is currently, I believe, I've got the 14th edition. I believe it's got the 15th edition is published. So it's been in print for quite a while. All right. Observational support, slam dunk fingerprints, solar nebular hypothesis or solar nebular theory. Planetary orbits. They're coplanar. They're all very much in virtually very close to the same plane as the Earth. The largest exception is Mercury, which is inclined about 7 degrees. They're prograde, so all the orbits are in the same direction, and they are generally circular. Once again, Mercury deviates the most from that circular pattern. So all 3 of those things we might consider to be predictions of the solar nebular theory. So this is where it gets just really interesting. Over here on the right, I've got a couple images of what are called protoplanetary disks. The idea is that there's some planets forming, these are kind of snapshots of, planets forming around a protostar. And then down at the right, that's an image of a binary. And so, again, foundations of astronomy, indicates protoplanetary disks are evidence for the solar nebula theory and how our solar system was formed. The rationale is that if solar systems come from disk, we expect to see disk. We do see disk. Here's evidence right here in images. Therefore, our system came from such a disk. That is invalid logic because there's no empirical continuity between the disk we observe today and the history of the solar system. So I give this one a star, but it's really a bit of confirmational bias in not telling the rest of the story. Observed exoplanets, this is the astronomy that's being done is just amazing. What is observed is generally bodies much larger than the Earth, generally very close to a star. And I put in parentheses there some information. Astronomical unit is the distance from the Earth to the Sun. So 1 is how far that distance is. So 0.3 is more like the distance of Mercury to the Sun, and that's what is commonly seen in these exoplanets. And the other thing is seen as these observed binary systems. This is a hard number to get a definitive, but they're over 50%. There's certainly a very large number of these binary systems which become very difficult to explain using the solar nebula theory. But we'll get into that a little bit more. But the point here is our solar system is not typical because of this lack of massive planets inside Mercury's orbit. The presence in orbit of Jupiter are extremely rare around a sun-like star. Now, to be fair with this statement, the solar system not being typical, and by the way, I'm pulling that from a couple of astronomers who've said that, is we may not have the technology yet to find these smaller rocky planets, so our sampling may be incomplete. So there's a little caveat to that statement. All right. So then the next one, again, our friends Seeds and Bachman say that isotopic gradient among the planets is evidence of their theory. Basically in blue on the graph for the interior rocky planets, the outer planets are more volatile rich with hydrogen and helium. That is based upon what's called the condensation sequence when the solar system was forming. The heavier metals condensated first near to the star, the sun, while as the larger gaseous planets condensated further away. Now, the issue there, of course, is this isotopic distribution. It's heterogeneous. There are gradients in the composition of the interior planets. And then the other thing that you can see here is that the sun is primarily hydrogen and helium. Then you go to your rocky planets, and then you go back to hydrogen helium. So you don't have a smooth gradient of composition that you might predict with a smooth temperature gradient radiating out from a protostar or young star. So again, it's probably a bit of confirmational bias. Look for the data that you want to, and maybe not get too excited about the data that is different from your worldview. Okay, here's where we are. We've talked a little bit about the observational support. Now we get into some physics. And we'll get into balloons and throwing up on rides at Six Flags. All right, so again, bear in mind, we're trying to use logic and not ideology, and we're trying to use observational and experimental science as we go through this. Okay, back here, this is where we're going. Now, under the radiometric dating model on the right, those over far right, you can see what we just talked about, the evidence that is a slam dunk or to some degree partially supports the solar nebular theory that we can see today. In red, those are problems that we talked about last time we talked about the radiometric dating model. I don't want to go into those today because we want to deal with the nebular theory. And what I'm going to show you is, and we have contradictory requirements in this system of star formation, ignition, and planet formation. And the three domains that we're going to be talking about is gas cloud collapse, stellar ignition, planetesimal formation. Now, this is not Vann's opinion. Here's a quote. "There's nothing like a generally agreed upon theory of star formation. The numerical challenge is to build simulations that include enough physics to go persuasively from the galactic scale to the point of resolving individual stars." So again, this is a mainstream physicist who is involved in modeling. So what is Mark Krumholtz talking about? To answer that question,
with the challenges, you mean, with the challenge,
yes,
of getting the math
the
to work.
challenges.
Yeah,
Absolutely. So, just a little context. We're talking about going from a molecular cloud to a star, to the sun. And so the point of this slide is to show the radically different conditions between the two. Like this first row, the temperature in a molecular cloud, again, according to our friends at Seeds and Backman, is 10 to 50 degrees Kelvin. Just to put that in perspective, room temperature is about 290 degrees Kelvin. So this is extremely cold. It's obviously near absolute zero. Then it's estimated in the center of the sun, 15.7 million degrees Kelvin. Maximum pressure, over 20 orders of magnitude greater in the core of the sun. Maximum density, again, over 20 orders of magnitude greater in the sun. So that's sort of just to give you a little context of, okay, we've got to come up with physics to get from point A, molecular cloud, to point B, a sun. And the conditions are dramatically different. That's the only point of this slide right here. Okay. I call this Observational Science 101. So the first thing to talk about is the ideal gas law. In PV equals ZnRT, basic physics class. So what if, Rebekah, what if you take a scuba tank? You've got a pressure gauge on it, and we take it into our lab, and we put it under a Bunsen burner. What's going to happen to the pressure gauge?
it'll go up, right? Because the warmer it gets, it'll be under more pressure.
Exactly. That's expressed in this equation. If we take this equation and we hold the volume constant, move it to the right side of the equation, and we increase the temperature, pressure is going to go up. Physics describes what we see, and we can predict it, calculate it. On the other hand, what if we take a balloon and put it under a Bunsen burner? What's it going to do in our laboratory?
I sorry, I got distracted by the chat. What was your question?
Oh, okay. So if we have a balloon and we take it into our
Yes.
laboratory, put a Bunsen burner under it, what's that balloon gonna do as we add
Explode.
heat
I
to
mean,
it?
burst, probably. Yeah.
That's right, it's gonna expand. And that's what this equation allows us to quantify. If you move the pressure over to the right side, increase the temperature, it's keeping the pressure the same, the volume goes up with temperature. So that's just some basic thermodynamics. Next is angular momentum. And this is a pretty big one. Angular momentum, first, just to explain it, motion in a straight line, momentum is mass times velocity. That's all it is. Now, circular motion about a point, say a planet orbiting a star, for example, basically that equation, L is angular momentum, is the mass velocity times the radius, how far that mass is away from the star. And then the law of conservation. This is, if you take the derivative of angular momentum with respect to time and there's zero external force, then that angular momentum doesn't change. In other words, you have to have an external force to change the angular momentum. And of course, the classic and obvious example is we have our ice skater. I don't remember what that's called when they spin really fast. But when they do that, they pull their arms in, the radius decreases, and then the velocity goes up to maintain the angular momentum. They put their arms out, the radius increases, the velocity decreases to maintain the angular momentum. So, does that make sense?
Yes.
Okay. All right. The next one is radiative cooling. This one's a little more, not the obvious example, but it's sort of described by the energy emitted by a body is proportional to the temperature. And that's in the lower right-hand side there, that equation. And then the other thing is what happens is when the density of a body increases, the opacity increases, and the amount of energy it radiates, that rate of energy release changes, it decreases. So these are the three basic physics things that if we sort of understand these, I think we can address the solar nebula theory. Okay. Bear with me a little bit. The purpose of this slide is to illustrate the contradictory conditions and amazing tuning required for cloud collapse, going from a molecular cloud to a protostar, and then for ignition of that protostar. So just taking that top row, the principle of thermal pressure, our known physics.
But Vann, before you go into it, I want to just tell people who are watching, a lot of people believe that, hey, we already know this, though. We know how stars form. Why are you guys even questioning this? Like, it's absolutely known how stars form. So would you like to address that, Vann? Because that is not true.
No, it's not true. I look in here, and for example, I mean, obviously they talk about this is how the stars collapse, but they omit this concept of thermal pressure. When it comes to angular momentum, they'll say, oh yeah, angular momentum is an issue, but we've solved that problem through magnetic braking. And that's all they say. And I think that is an example of conformational bias, a refusal to admit that our physics doesn't match up with our theory. And this is what I would like to, again, thank you to your listeners for sticking with us this long. This is what I would like to address.
Great. Thank you.
Okay.
So thermal pressure.
Thermal pressure. During the collapse, compression, the temperature goes up as gravitational potential energy is converted to temperature, and pressure is a function of temperature. So as the pressure goes up, that resists further collapse. This is the issue of putting that balloon under the Bunsen burner. When you heat it up, what's it try to do? It tries to expand. It tries to resist collapse. And so the condition that's needed for collapse is shedding thermal energy, which decreases the pressure, allowing that gravitational infall. But the contradiction is for ignition. For core ignition, you have to get to over 15 million degrees, so you've got to retain core thermal energy, allowing that temperature to rise to that fusion threshold. And so I've put these little red symbols here to illustrate the opposite requirements. So in other words, if you don't shed the thermal energy, you're not going to collapse. But if you shed the thermal energy, you're not going to ignite. So the next one, and again, this is just basic physics. The next one is conservation of angular momentum. And this one is, as the cloud radius decreases, the angular velocity increases, and that resists further collapse. So do you remember, like when you went to Six Flags, Rebekah, would you get on the rides do you remember that one? It was like this cylinder, and you would go stand in it, and it would spin around, and then the bottom would fall out?
Yes.
Yeah, and then I puke on the guy next to me. But this is what this principle is of angular momentum. When you have that increasing angular velocity as your cloud collapses, it resists collapse. It's like, how hard is it to, while you're spinning around, to hold your arms out kind of deal. And so again, here the condition for collapse is you have to shed angular momentum to prevent that centrifugal support, allowing that gravitational infall. Now, for ignition, you have to do the same thing. These actually are aligned. You have to shed angular momentum to allow a symmetric central compression and heating. So we'll come back to this one, but this is sort of describes what needs to be addressed with respect to conservation of angular momentum. Radiative cooling, if you increase the temperature, you increase the rate of energy loss, but it becomes inefficient with this increasing opacity during collapse. Again, this is sort of the condition you need for collapse, is you've got to radiate the energy fast enough to allow the infall, and then ignition, you've got to retain that core thermal energy. So this is, again, kind of contradictory conditions, but it's also a tuning problem. Somehow you've got to tune these so that this event happens. Okay. Thank you for working through that slide.
Hey, that looks like a lot of problems in star formation. So I hope those who are watching, like I said, if you think young Earth creation is improbable because of things like the heat problem, check your own backyard. What about star formation? What about the formation of the solar system? These are problems, very big problems, but Most people never even doubt it. They just get told this is the way it happened. They believe it. So if you want, people like me to be critical thinkers, are you also being a critical thinker? So go ahead, Vann.
No, that's well said, Rebekah. I mean, the challenge is to know what you believe and why you believe it, I think. So here, let's talk just briefly about planet formation uncertainty, and then we'll put it together with the stars. Here's a quote. Again, these are mainstream guys. This isn't just Vann's opinion. This is a recognized problem. Oh, by the way, this is really cool. This is Saturn. It's got this hexagonal feature in the North Pole that is just super cool. So anyway, here's what these fellas said. Mm-hmm. The origin of the planets is a vast, complex, and still quite a mysterious subject. It is still not clear how the planets of the solar system formed. Our solar system is not a typical case, and categories of planets do not exist in our system or common elsewhere. This was written in 2016. This is the science. This is an astronomer and astrophysicist who are saying this. All right. So, what are they talking about? What's the problem? All right. This is the problem. Gravity is too weak to build, but strong enough to remove. This is kind of interesting. There's three observations. And you remember when I was talking about planet formation, you've got these dust particles and they kind of electrostatic forces, they stick together, and then as they bump into each other, they stick together, and they gradually get bigger and bigger and bigger until they form a planetesimal, which is defined notionally as about 1 kilometer across. All right. There are 3 observations that make that planetesimal extremely unlikely. The first is called the bouncing barrier. Collisions between millimeter-sized particles often results in them bouncing off of each other. So what that means is the repulsive forces exceed the gravitational attraction between those particles. Pretty simple. Fragmentation barrier. Collisions between sub-meter-sized particles often result in fragmentation. As particles theoretically get bigger, you've got infall, and you've got particles bouncing off each other. The kinetic energy of the collisions increases during the collapse. And so, again, the repulsive forces exceed gravitational attraction. Then, angular momentum comes into play when you get to about a meter-sized particle. And then, of course, this is physics calculations, basic physics calculations, because what happens is these meter-sized objects experience drag in the gas, and that leads to a loss of angular momentum, and that these meter-sized objects then spiral into the protostar. So again, in this case, gravitational attraction exceeds angular momentum. So that's sort of what I mean by gravity is too weak to build, but strong enough to remove. All right. We're going to tie it all together with this slide right here. This is the exact slide that I showed you before, but on the right, under that blue column, I've added the conditions for planetesimal formation. So these are sort of the 3 domains we need to talk about. And by the way, I'm only talking about, 3 observations. There are additional issues that have to be overcome in order for collapse to result in planets. But anyway, again, up at the top, you've got that thermal issue. We talked about the contradictory conditions for collapse and ignition. For planetesimal formation, you've got to shed energy to allow that aggregation of these in the inner disk to allow for cold, stable zones, so that your silicates, your heavier elements can form. Angular momentum. Gosh, you have to shed angular momentum as a condition for cloud collapse and a condition for ignition. But you must retain angular momentum in the aggregates in order to theoretically form a planetesimal. So you've got contradictory conditions. And then finally, you've got this radiative cooling that we talked about. On the one hand, you have to radiate for cloud collapse. If you don't do that, you don't collapse. And you have to retain core thermal energy for fusion ignition. If you don't retain core thermal energy and you radiate it, you don't ignite. And then, of course, the condition for planetesimal formation, you've got to radiate that energy away, allowing those elements to solidify. So again, the point of this slide is, in order for planets and stars to form, you've got contradictory conditions based on basic physics. Okay, we're going to start to wrap it up here, and we're going to get to some implications, which I hope will be very interesting. Again, we want to make observational conclusions. We want to try to stick to logic. We want to stick to gravity, thermodynamics, and conservational laws. And so what we can safely say is star formation is improbable, that gravity is an insufficient mediator, if you will, for those contradictory and tuning conditions that are needed for collapse and ignition. Planet formation, improbable, because of the submeter aggregation issue, and then we have to retain them in orbit. We have to deal with angular momentum to form those planets. We've got binaries and exoplanets, which totally blows, a spherical collapse model of the solar nebular theory. It's inconsistent. And so finally, of course, what we've talked about is the incompatibility among thermodynamic and angular momentum requirements. Once again, there's nothing new here. Mainstream physicists, if you go look beyond the textbook, if you go search it out in technical papers, you will find these issues. This is nothing new. Okay. So here we go. What are the implications? Because someone, I imagine, at least one of your viewers has said, Vann, stars and planets are observed. Well, what that means is the solar nebula theory is either false or unknown physics are needed to overcome these incompatibility and fine-tuning issues. Or an alternative cosmology is needed, or God created the universe.
Ding, 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 ding. I think that final one is the best answer. But I like this. So what people are saying a lot in the chat is, well, just because we don't know right now how it works, that's just, we're still figuring things out. So here you're leaving open the possibility that we could find some properties of physics that we didn't understand before that allow for it. But if you want to follow according to, or if you want to be the most scientific about our observations right now, what do you think we should conclude about our scientific observations right now?
There's a pretty open question. Yeah, so okay, if you're relying on future discoveries, that sounds like faith to me. And then it also sounds like there's not a logical theoretical basis for billions of years. That sounds like an acknowledgement of that as well. Uh, and I have, we'll talk about this a little bit more. The suggestions that I have for our materialist friends uh, is there may be an alternative cosmology that'll give them a little bit better answer. But anyway, I God created the universe is a valid option in this logical domain here. Physics hasn't disproven God, I guess, if is what I would say. All right, so let's go back because your question kind of leads back to our table where we were talking at the beginning. The standard is observational, experimental, beyond a reasonable doubt, because that's what these guys say. Billions of years is a fact. And it doesn't measure up. I think when you look at the solar nebular theory, you classify it as speculative. It's in the same realm as inflation. It's non-falsifiable, and it appears to be an ad hoc theory designed to solve these anomalies, this tension in our physics, and so because of that, that means that radiometric dating doesn't have a foundation for its assumptions on its inputs. And so I think you link the two and say grand jury denies indictment. And again, this is all within the realm of logic and observational and experimental science. Okay, so sort of wrapping up here, this is what we talked about. The evidence doesn't support 235U and 238 assumptions. Solar nebula theory, as we talked about, we've got contradictory requirements necessary for the three main domains: collapse, ignition, and planetesimal formation. And those are all within known physics. And then the assumptions on radiometric dating model, we've already talked about those. So let's circle back. We've got this ancients theme. Let's go back to it. I'm going to suggest to you that the assumption of U235, 238 is circular reasoning. This is the way I would say it. The age is billions of years because of 235U and 238U inputs. Well, 235U and 238U are inputs because the age is billions of years. This is circular reasoning, tends to be common in the face of uncertainty. Because remember, we're trying to make a backward forecast about the age of the Earth. All we know is what we can observe right now. There are no measurements in the past to constrain our model. And so it tends to lend itself to this circular reasoning. And so my take is, let's look at it from a different side. I could say God created the universe and used these 7 isotopes. Those are that lower row there. Those were present at creation, And the result is something like 6,000 to 8,000 years. I'm using circular reasoning as well in terms of the scientific, this approach that we're talking about. I would be guilty of making a non-falsifiable statement, just like our friends who say use U-238, U-235, and say 4.5 billion years. If I'm using logic and science, there's nothing to choose one of the other, if that makes sense to you. If I just put on my blinders and try to look at it from a purely logical standpoint. All right.
Cool.
On this ancient theme, I couldn't resist Cicero. Everybody's gotta love Cicero. He was a Roman senator, defender of the Republic when the Republic was going out of vogue, a philosopher. He said, this is 2,000 years ago, by the way, can any sane person think that all this grouping of stars and this vast ordering of the heavens could have resulted from atoms coursing to and fro fortuitously and at random? Isn't it fascinating that 2,000 years later, with all of our science, the core of our arguments are basically the same? So, all right, let's wrap it up. And I know your listeners are like, thank goodness this is the last slide. Age of the Earth is unknowable using radiometric dating. It's not like using a decibel meter at all. It's a model that's making a forecast into the past. Its age estimate is entirely dependent upon the inputs. Solar nebula theory is false or needs unknown physics for viability. Therefore, the 235, 238 assumption used in radiometric dating is circular reasoning. Now, what I would leave our materialist friends with is recognize the uncertainty. Build a numerical model for yourself and run it using Patterson's methodology with those different inputs. And you'll see that the output varies. Know what you believe and why you believe it. And another thing I would say is, escape the chains of the 18th century. Gravity doesn't cut it. It's a dead end. You've got to come up with an alternative cosmology to support a materialist narrative. Now, for the Christians, I would say you do not have to accept billions of years, because billions of years is not a fact. It's a forecast. You do not have to believe some parts of the Bible are true and some parts of the Bible are false, because it's written that all scripture is God-breathed.
Cool. Thank you, Vann. Now, I was going to put this question up. So Andrew said, can he elaborate why uranium lead dating is circular? Perhaps I missed that bit. And this presentation that Vann is giving is based on our previous talk where he went into this very deeply. And later after the stream, I will put the link for that in the description so that any future watchers can easily find it. But so I know you don't want to repeat the entire 2-hour presentation that you did on that, Vann, but can you sum it up for Andrew?
Yeah, and in fairness for Andrew, I referenced that presentation I did before and made some statements based upon it. And uranium lead dating is circular because it's billions of years old. I've got to use U-235 and U-238 in order to get that result. Or to flip it around, If I use U-235 and U-238 as initial inputs into radiometric dating, I get billions of years. So it's the definition of circular reasoning.
Well, and I think the thing that people also did not hear was when you talked about how, look, people are often who are familiar with the radioisotope dating will say that we know the decay rate of uranium to lead, and we know that lead is excluded from zircon when it's being formed. Okay, and Vann did address this. I'll address it really quickly. So that is in the condition of the not in the condition of the formation in plasma. And Vann showed how even there's another substance that I forget the name of it, trolite or something. Was it trolite? Okay.
Yeah.
Anyway, it excludes lead under a certain condition. But if lead is hot enough, like in the condition of plasma, it can actually change to like lead, like a positive, like +4.
+4.
And +4, and then it will be incorporated into the zircon. So the whole point is we don't actually know the initial conditions. And we're assuming when we see the amount of lead in there, we're assuming based on this, exclusion of lead, we're assuming that we know the initial condition, but we don't. And so that's the whole point that Vann was making, is that we actually don't know the initial condition. And you can put in a number of factors. You can make the initial condition based on what you make the initial condition. You can make the age of the Earth any age, including 8,000 years old.
Well said.
Thank you. Okay, Andrew had another thing. So, okay, he says this is why lead isochrons are useful for meteorites and old Earth rocks. You don't need to know the initial amounts, just that the solar nebula was isotopically homogeneous. Do you have a response to this?
Yeah, on a couple levels. It's Patterson in his landmark paper assumed that one reservoir is a source and assumed that the lead was constant, was homogeneous, but the uranium was variable. So that's not even an assumption that Patterson used. And then secondly, you have to know the initial amounts. Even if you assume nothing changed during the transient conditions, you have to know the initial amounts. The only thing I can suggest to Andrew is just run the calculations yourself and see what you get.
Thank you so much. Okay, did you have any final thoughts you wanted to share?
No, that's all I've got today.
Okay, because I there were other comments and things in the chat, but I mostly brought them up throughout the presentation. So I think, anyway, this was a great presentation. Thank you so much. So I hope for those who are watching, this has at least given you a reason to question the model of the formation of the solar system that's taught in all the textbooks, but has some serious flaws to it. And like I said, and Vann said, you don't have to take a creationist's word for it. He's getting this from mainstream science. So you can Google it yourself and find out, are these problems that he brought up really problems for solar system formation? You'll find that they are. And so, why is it still believed? It's believed because it's the only naturalistic explanation we've got. So there is another option, though. You don't have to believe that it formed by natural processes. You could believe that God created it and that it does not contradict science. It is perfectly reasonable within science to believe that God created. In fact, we have good evidence that God created, because when we look at the properties of life and the orderly universe, it's good evidence for an intelligent designer. Well, okay. Thanks for your time today, Vann. And thanks everybody for watching. I appreciate your support. This is a small channel, but I've been really encouraged to see that the numbers of viewers are going up. And I really appreciate when people who disagree with my perspective are willing to engage. So thank you.